All right, now let's move on to a similar yet slightly different set of examples. The next couple examples are going to involve money. Just like population, money follows the law of exponential growth and decay because the more money I have in an account, if I'm earning interest at a particular rate, 2% of $1 is very different than 2% of $1 million. So the more money I have in the account, the faster it's actually going to grow. Thus, anytime we're talking about interest in an account, you can follow the law of exponential growth and decay. So here we have $4,000 invested in a mutual fund with expected return of 8%. For those who aren't aware, you can think of a mutual fund as kind of a cross between playing the stock market and a savings account. It's as if you're putting money into a savings account, but the savings account is going to do better the better the stock market is doing. So that's why it says expected return of 8%. If the amount of money grows at a rate proportional to the amount present, there's the law of exponential growth and decay. How much money will be expected in the account after 10, 25, and 40 years? So here we actually have three separate questions that are being asked, so you need to make sure that you present three separate answers. Now, since it said that the money is growing at a rate proportional to the amount present, we can start with the law of exponential growth and decay, y equals CE to the KT. The 4,000 represents the initial amount. We'll plug that in for C, but it doesn't give me a secondary value because instead it gives me this percentage, 8%. Now that's actually a good thing because that 8% actually represents my K value. Recall that in the law of exponential growth and decay, C is your initial amount and K is your growth or decay rate. Well, if you're getting an interest rate of 8%, that would be your growth rate. Now also keep in mind we're never going to use a percentage written as a percentage in a math problem. We're always going to convert that decimal. 8% really means 0.08. So we're going to take that 0.08 and plug it in for K as well as the 4,000 for C. Now for those of you who have seen this before, which should be everyone, there's another version of this formula when it comes to money, and that's A equals PE to the RT. P is the principal amount that you start with, in other words the C value, and then R is your interest rate, in other words 8%, and T is still time. So when it comes to money, sometimes you'll see the formula written as Y equals CE to the KT. Other times A equals PE to the RT. That's just your exponential growth formula for compound interest versus this is the law of exponential growth and decay. It's actually the same formula either way, so if you look this up in other resources, it's the same formula. So 4,000 e to the 0.08 t. There were three questions. What's the amount in the account after 10, 25, and 40 years? So take a moment, type this into your calculator one at a time, plug in 10, 25, and 40 for t. Pause here, play when you're ready. So y of 10 would look like this. Type it into your calculator. You should get about $8,900. Keep in mind we're talking about money, so I'm only going to give 2 digits past the decimal to represent dimes and pennies. At 25 years, it's going to get up to $29,000, and at 40 years, it's going to be almost $100,000, $98,000. Consider if you are nearing 20 years of age, if you're able to save up $4,000 by the time that you turn 20 with a part-time job, shouldn't be that difficult. And then investing that into a mutual fund when you turn 20 years old, and just letting that money sit for the next 40 years of your life. At 60 years of age, you can go finally withdraw from that account an extra $100,000 that you hadn't planned on having. Wouldn't that be nice? Remember, the earlier you start saving for retirement, the more money you're going to have when you actually get there. Speaking of saving for retirement, here's another example. Based on what we know, why don't you go ahead and give this one a try. The only interesting piece of vocabulary here is this part about being compounded continuously. That's just a fancy way of saying use the law of exponential growth and decay. Pause here, play when you're ready. All right, $72 placed into a savings account at 1.25% interest. Account is compounded continuously, so y equals CE to the KT. How long will it take for the amount to reach $1 million? So we're looking for a time when the output is 1 million. We start with 72, so that's our C value, and the 1.25%, that would represent our K value. Recall that we need to convert that to a decimal before we plug it in. So 1 million equals 72e to the 0.0125 t. The goal is to solve for t, so we'll follow the rules of solving an exponential equation. Start by dividing by 72, simplify if you wish. Take the ln of both sides. That's going to be ln of 1,000,000 over 72 equals 0.0125 times t. Divide by the 0.0125, and I get this as my exact answer. Type in the calculator, we get about 763 years. Keep in mind, money grows at a rate proportional to the amount present, so if you want to become a millionaire a little bit quicker than 763 years, maybe start with something larger than $72. Now, all the examples that we've looked at thus far have all been examples of exponential growth. The next few examples are going to be examples of exponential decay. One of the very common examples that I like to use is the concept of half-life. If you're taking a physics or chemistry class, you may already be vaguely familiar with the concept of half-life. Let me give you a quick definition before we move on. The half-life of an element is the amount of time it takes for a radioactive substance to decay to half of its original amount. Now, there are certain elements that we commonly know as being radioactive, like uranium, plutonium, stuff like that that's used in nuclear weapons and used in nuclear power plants. But technically, everything is radioactive. What radioactivity means is that an element is expelling energy from the element itself. It's taking its own mass and using E equals mc squared. Mass is a form of energy. As it sends off energy, it's reducing its mass. Now, a proton, for example, has a half-life that is measured in trillions of years, and the universe has only existed, as far as we know, about 13 billion years. So it's hard to measure the radioactivity of a proton when we're talking about those types of timescales. But other types of radioactive substances have much smaller, much shorter half-lives, so they're much easier to measure, and because they're sending off more energy in a shorter period of time, they're much more dangerous to us as humans. Hydrogen is radioactive, but not in a way that's dangerous to me. Plutonium is radioactive, and it can kill me pretty quickly. So, again, the half-life is simply the predetermined amount of time that it takes for any given element to decay to half of its original amount. Beautiful thing about the periodic table is it's predictable. Every particular element has a known half-life. That's just one of the basic properties of those particular elements. And we can use that in a predictive way. And by understanding the concept of what half-life is, if I tell you the half-life of a substance is a particular number of years, well, we can start with the idea that at time 0, you have whatever the initial amount was, let's call it C, and then for this substance in example 7, I told you that the half-life was 1200, which means our secondary piece of information is that after 1200 years, there will be half of whatever C was left. So if I give you the initial amount and I tell you what the half-life is, the half-life implies what the secondary amount will be. So, let's take this example and apply the law of exponential growth and decay. You start with 108 grams. How much is left after 420 years, keeping in mind that the half-life is 1200 years? Well, our initial amount is 108. After 1200 years, we're going to have half of that left, so 54 will be our secondary amount. And then the question is asking how much is left after 420 years. Notice how this problem looks just like any of the population problems that we did earlier. The only difference is how we interpret that given information. So I'm going to go ahead and suggest that you pause here and then hit play when you're ready. So, plugging in the information that we have, 54, 108, and 1200 appropriately. Divide by 108. Now, normally I would just leave it as 54 over 108, but since I figured out the 54 by cutting the 108 in half, when I divide, I'm just going to go back to that 1/2. One of the things I sometimes like to do on these half-life problems is instead of writing 54 at all, I'm just going to write 1/2 of whatever the C value was, so that when I plug it in, 1/2 of 108, and I go to divide by 108, the 108 cancels out and I'm just left with 1/2. That way I never actually have to calculate what half of 108 happens to be. When it's easy, great, but when it's not so easy, maybe it's nicer to write it like that. ln both sides, I have ln of 1/2 equals 1200, so k equals ln of 1/2 over 1200. Taking that, plugging it back into y equals ce to the kt to build my model. Recall that my shortcut when it comes to e to the ln, allows me to cancel the e and the ln and bring the 1/2 downstairs, and I have my prettier version of the model. Now the question says how much is left after 420 years. Plugging in 420 for the t value, type that into a calculator, we should get about 84.735 grams. Notice how the answer that we got is actually more than half of the original amount because we only waited 420 years. We didn't wait the full 1200 years to get half of the original amount. So the answer I expected was something between 100% and 50% of what I started with, 84 being somewhere in that region. All right, let's look at a slightly different version of that question. How long will it take to decay to 1/3 the original amount? Notice I'm still starting with 108, and I'm still starting with that same basic model. Go ahead and pause here, hit play when you're ready. So I'm looking for how long it'll take to decay to 1/3 the original amount. How long is t? We're solving for t when y is 1/3 of 108. Now I could either just write that as 1/3 of 108 and plug that in and allow the 108 to cancel out, or I can recognize, oh, 1/3 of 108, that's 36. So 36 equals 108, but when I divide, I'm right back to 1/3. That original amount actually doesn't matter. Regardless of what that original amount, it's going to take the same amount of time to decay to 1/3 of the original amount. Goal is to solve for t, so I'll use a logarithm, bring the exponent up front, multiply by 1200, divide by ln of 1/2. I have my exact answer, type it in a calculator. It's going to take about 1900 years to decay to 1/3 the original amount. Keep in mind 1/3 is less than 1/2, so it makes sense that it would take more than 1200 years. Also, 1/3 is greater than 1/4. If I wait 1200 years, I'll have half of the original amount. If I double that and wait 2400 years, I'll have a quarter of the original amount. In other words, half of a half. So 1900 years seems reasonable because 1/3 is between a half and a quarter, and 1900 is between 1200 and 2400 years. So I'm getting my answer, but I'm also thinking about whether that answer is reasonable. All right, still using that same 1200 years as my half-life, but let's change up the question a little bit. This time, forget what the original amount was on the first two parts of this question. What was the original amount if there are 5 grams left after 2300 years? So in this case, we still have that model that we built from the previous two problems, but remember what I told you a second ago, that original amount actually doesn't matter as far as how long it takes to decay to a certain percentage of the original amount. That original amount is always going to divide out and becomes irrelevant. So in this case, I'm just going to define my initial amount as c, and that c is the value that I'm looking for as the answer to this question. I know that after 2300 years, there's going to be 5 grams left, so y of 2300 equals 5. And I also know that I can use the model that I had in the previous examples. The only difference is, instead of writing 108 for c, I'm going to leave c as c. Now, a little shortcut going forward, anytime you're doing a half-life problem, this is always going to be 1/2. And this is always going to be the half-life. So if you want a shortcut, you are welcome to use this shortcut. If it's a half-life problem, it will always be c times 1/2 raised to the t over the half-life. So if I tell you substance decays with a half-life of 342 years, then I could actually set it up as 1/2 raised to the t over 342. Just so happens that it works out that way 100% of the time. Feel free on half-life problems, instead of starting with y equals ce to the kt, you can just start with the half-life specific version of the law of exponential growth and decay. All right, so back to the formula that we're working with here. Half-life is 1200. It's a half-life problem, so the base is 1/2. C is unknown, plugging in 5 and 2300 for y and t respectively. The goal is to solve for c. Now keep in mind, focus on the equation that's in front of you and use an appropriate technique to solve the equation that's in front of you. Just because we've been using logarithms on every single problem so far does not mean we're going to use a logarithm on this one. We use a logarithm to solve an exponential equation. Look at what we have here. This is not an exponential equation. The variable is not part of the exponent. The variable is c. C is being multiplied by the number 1/2 raised to the 2300 over 1200. This is not an exponential equation. I do not need a logarithm. The goal is to get c by itself. C is being multiplied by a number, so divide by that number. Divide both sides by 1/2 raised to the 2300 over 1200, and I get 5 over 1/2 raised to the 2300 over 1200. Type that in your calculator very, very carefully, and if you type it in correctly, you should get about 18.877. So a substance with a 1200-year half-life that has 5 grams left after 2300 years must have started with 18.877 grams. All right, here's another half-life question. Pause here, hit play when you're ready. All right, this time we're actually looking for the half-life. So since I don't know what the half-life is, I'm going to suggest that you not start with the half-life version of the formula. If I know what the half-life is, then I'll start with the c times 1/2 raised to the t over the half-life. But in this case, there's too many unknowns to start with that formula. So we're just going to start with identifying our given information. Initial value is 50. Secondary value is 20 minutes, 17 grams. And we're looking for the half-life of the substance. So because I'm looking for the half-life of the substance, half-life is the amount of time that the y value becomes half of the original amount. Well, the original amount was 50, so half the original amount is 25. So using that information, let's plug it into my formula y equals ce to the kt. C is 50, t is 20, and y is 17. We're going to use that to solve for k. Divide by 50, ln both sides, divide by 20, and we get our k value. Taking the k value, plugging it back into the formula to get our initial model. Simplifying this, bring the 17 over 50 downstairs and leaving t over 20 upstairs. I get my simplified model. The goal is to determine the half-life. So if I started with 50, I want to know how much time is it going to take to get to 25. So let's divide. 25 over 50 is, of course, 1/2. ln both sides, bringing the t to the front. Multiply by 20, divide by ln of 17 over 50. And type that into a calculator. So the half-life of this substance, because we started with 50 grams and we had 17 grams left after 20 minutes, the half-life is approximately 12.850 minutes. All right, let's look at another example. Now, don't get scared away too quickly. I'm throwing this problem in here basically just for fun. A very common application of half-life is the idea of carbon dating. Now, I assume at some point in your life you've heard the concept of carbon dating. What we can do is figure out how old an object is by measuring the amount of carbon in that object, because of course we are all carbon-based life forms. You have carbon in you, your parents have carbon in you. If you have a dog, the dog has carbon in it. Carbon is the building block that life uses to build more life. Now, while you're living, you are adding more carbon into your body by consuming food. But once you stop living, you no longer continue adding carbon into your body, and the carbon that's already in your body begins to break down because it has a half-life of 5,730 years. And by measuring the ratio between different types of carbon, for instance, carbon-14 is the one with a half-life of 5,730 years, versus another type of carbon called carbon-12 has a much longer half-life. And by measuring the percentage of carbon-14 in your body compared to carbon-12, scientists can predict exactly how old something is. So let's look at this example. Carbon-14, again, has a half-life of 5,730 years. You are presented with a document which purports to contain the recollections of a Mycenaean soldier during the Trojan War. The city of Troy was finally destroyed in about 1250 BC, or about 3,250 years ago. Carbon dating evaluates the ratio of radioactive carbon-14 to the more stable carbon-12. Given the amount of carbon-12 contained in a measured sample cut from the document, there would have been about 1.3 times 10 to the negative 12 grams of carbon-14 in the sample when the parchment was new, assuming the proposed age is correct. According to your equipment, there remains 1 times 10 to the negative 12 grams. So again, it would have had 1.3 times 10 to the negative 12th when it started. Now it has 1.0 times 10 to the negative 12 grams. Is there a possibility that this is a genuine document? Or is this instead a recent forgery? Justify your conclusions. So, someone has what they're claiming is a document from the Trojan War. We know how long ago that would have been. We can carbon date the document to see exactly how old this document is, and then we can decide whether it's actually from the Trojan War or if it's something more recent. So let's start by identifying the important information, because I don't want to have to keep reading through this statement over and over again. Let's start with a half-life of 5,730 years. So at time 0 we have C. At time 5,730 we're going to have half of C. Going back, if I keep reading, I see more important information. The 3250 years ago, that's the age that I'm hoping this document comes out to be, so we'll keep that information in the back of our minds for later. More important right now would be the 1.3 times 10 to the negative 12th. Remember, that's how much, based on the carbon 12, that's how much carbon 14 the parchment would have had when the parchment was new. So that's our C value. So we can replace C with 1.3 times 10 to the negative 12th. And here, I'm not going to bother multiplying. I'm just going to say half of 1.3 times 10 to the negative 12th because, again, I know it's going to cancel out anyway. Keep reading. According to your equipment, currently there is 1.0 times 10 to the negative 12th. And what I'm trying to figure out is how much time has passed between the time there was 1.3 times 10 to the negative 12th grams and 1.0. So I'm looking for the t value when y is 1.0, given that c is 1.3. Now that we have the information, we can build our model. Y equals ce to the kt. C is 1.3 times 10 to the negative 12. And then plugging in the 5730 and the 1/2 1.3 times 10 to the negative 12. Let's solve for k. Keep in mind the 1.3 times 10 to the negative 12 immediately cancels out. ln both sides, divide by 5730. We have our k value. We can go back and fill in our k value to our model, and then we can simplify our model. Keep in mind, this was the shortcut I told you about earlier. We could have started the problem right here. C value is 1.3 times 10 to the negative 12, 1/2 t over 5730. If you had skipped all those previous steps and just started right here, you are perfectly fine. So now the goal is to solve for t when y equals 1 times 10 to the negative 12. So let's use the same process that we've always been using. It doesn't matter that the numbers are hideously ugly. Use the same process that we use every single time. The goal is to get t by itself. So I'll start by dividing by the c value. And notice when I divide by the c value, the 10 to the negative 12th actually cancels out completely. And we're left with 1.0 over 1.3. ln both sides. Bring the exponent to the front. Multiply by 5730 and divide by ln of 1/2, and we have our exact answer. Type that into a calculator, and I get this. So based on the information that I have, I can predict that this document is about 2,200 years old. But remember, it said here that the Trojan War occurred a little over 3,000 years ago. So if the document is only 2,200 years old, that means it's a fake. Now, it still is 2,200 years old, so it's an interesting piece of interesting artifact, but it is not from the Trojan War. That was fun. Let's do one more fun example. Pause here, play when you're ready. So here's an example that's near and dear to my heart. After whiskey is distilled, it is aged in a barrel until it is ready to sell. As the whiskey sits, it will evaporate over time. Just in case you're curious, that part that evaporates is referred to as the angel share. If a given barrel of whiskey evaporates at a rate of 2% per year, how much whiskey is left after 12 years? So, let's start with our law of exponential growth and decay. And what do we know? Well, typically I'd want to know how much whiskey that we're starting with. But it never actually tells me how much whiskey I'm starting with. Or does it? It says if a given barrel. So we are starting with exactly 1 barrel. So one way you could do this problem is starting with a C value of 1. Then it also says that it evaporates at a rate of 2% per year. That allows me to figure out my secondary value. So if I start with 1 barrel, my secondary value would be 1 barrel minus 2%. After 1 year, t equals 1, we would have 2% less of a barrel. Now here's where things start to get a little confusing, is the units that we're measuring in. the C value is measured in barrels, but then your secondary value is measured in percentage of a barrel. So here's my suggestion. Because of those percentages in there and because our initial value is exactly 1, here's what I'm going to do. I'm going to define my initial value to be 100. In other words, 100%. I'm starting with 100% of my barrel. After 1 year, I'm going to have 98% of the barrel because I lost 2%, so 100 becomes 98. How much whiskey is left after 12 years? So when T equals 12, how much of the barrel is left? So that will allow me to answer the question in terms of a percentage of the barrel because the Y values are defined in terms of percentages. So now that you have that information in hand, if you want to pause here and continue, hit play when you're ready. So 98 equals 100 e to the k. Keep in mind the t value in this case would be 1 when y is 98. Divide by 100 and take the ln of both sides. So k equals ln of 98 over 100. Plugging that back into the model and simplifying, we're going to get 100 times 98 over 100 raised to the t. Plugging in t equals 12, here's my exact answer. Type that in the calculator, and I'm going to get about 78.471. So there's about 78% of the barrel left after 12 years. Slancha.